It is our pleasure to host Dominic Catanzaro from Stanford University today for QuIST seminar. Dominic did his undergraduate in applied physics at Caltech and is pursuing a PhD in electrical engineering at Stanford University in Jelena Vučković Group. And he has done some very impressive nanofabrication work with color centers and silicon carbide, and we're looking forward to learning from him.
Thank you. And thank you all for coming. It's an honor to speak here. My name's Dominic. I'm from Jelena's group. And today I'll be speaking about electrical control of silicon carbide cavity QED systems. And I'd like to start kind of with some motivation from almost 50 years ago now, which is Richard Feynman, a very well-known quantum physicist. And he's mentioning here that we live in a quantum mechanical world. And because we live in a quantum mechanical world, to really simulate, to compute things, we can't really use classical stuff. And as he said, it's a wonderful problem, and it doesn't look easy. And my PhD has certainly not been easy. But I am excited to share with you what I've done in it anyway. And I'm going to start off with, there are a number of experimental platforms for doing quantum computing, quantum simulation, superconducting qubits, neutral atoms, trapped ions. But really, this talk, as you can kind of tell from the title, is going to be about solid-state defects, specifically those hosted in silicon carbide. But the thing is, there's all of these different platforms right now because nobody's really quite sure which one is the best for any specific application, sensing, computing, simulation, all of this. And so they all have different strengths and weaknesses. And hopefully today I can tell you a little bit about the specific strengths of the silicon carbide platform. So really where the solid state defects kind of shine when it comes to quantum information and quantum computing is in spin-photon entanglement. So the defects themselves have relatively long spin coherence times because the spin coherence times are long, and because you can couple nearby nuclear spins in the solid-state platform to the electron spin, you have these very long-lived nuclear spin registers, several qubits all coupled to an electron spin. This electron spin, because of the nature of the defects that we've chosen, is optically addressable. Because this is optically addressable, you can generate spin-photon entanglement by entangling the photon that talks to the electron spin with the electron spin, and then therefore the nuclear spins. Because you can swap entanglement from the electron spin to the nearby nuclear spins via just microwave drives at a local kind of level. And as a result, we can make this nuclear spin register around an electron spin. That's several qubits right there. And then if you put this entire system in an optical cavity, you can then couple the photons from, not only can you increase the coupling strength between photons and the electron spin, but then you can also have them interact with other electron spins through the cavity, mediated through the optical cavity. And as such, you can envision building some sort of quantum register where the cavity mode talks to the electron spins talk to the nuclear spins, and then the cavity mode can be extracted and sent through an optical fiber off to other places, and to build this wonderful network. And so that's kind of the dream, but of course this is still a long ways away. And so today I'd like to focus on the center part here, which is where I believe cavity QED really shines when it comes to talking to optically addressable electron spins through the cavity mode. So in this case, having high fidelity cavity QED systems really enables this giant architecture that I was talking about before. And this is where I believe the solid state platform really shines, is in doing cavity QED. And that's because we can leverage the scalability that has been, people have worked on developing nanofabrication techniques in solid state platforms for, I guess, 80, almost 100 years now. Because of this, we can leverage nanofabrication to do excellent photonics. So we can control the photonic modes in a way that allows for much more complexity for a cavity QED system than perhaps free space cold atoms or trapped ions would require. The long spin coherence times, like I mentioned before, let us do store quantum states for a long period of time, and we also, in another significant advantage of the solid state is that there's a bulk nonlinearity inherent to some solid state platforms, and this also enables us to reach complex Hamiltonians that we couldn't talk to before. And so that means we can kind of simplify that wonderful Blender image down to something that looks a little bit more like this, where we have individual electron spins, two like optically addressable spin states that are coupled to a optical cavity mode, A here, and we can, if we're looking at studying cavity QED in solid state platforms, we're really looking at controlling the individual coupling strengths of all of these defects to the cavity mode. We're interested in controlling the phase of this interaction in G. We're interested in controlling the loss rates from the cavity mode out to other systems or out to the environment. And while we can't really control the individual loss rates and inside the kind of spin defect centers, color centers themselves, we can choose color centers that have level structures and rates that are going to be more interesting. But this, of course, requires controlling all of this. And in a solid state platform, this is somewhat difficult, because if you compare it to, for example, neutral atoms, the neutral atom qubit, in this case, would be our electron spin in our color center. Neutral atoms are all the same. Every single one of them is identical. And so you load it, and you know it's going to be exactly the same frequencies. They're going to be exactly the same place. They all behave identically. But because our solid state qubits are within a messy lattice, relatively messy lattice, they're all going to be kind of different. They're all going to be in slightly different spatial locations. As a result, our coupling strengths to our cavity modes are going to be slightly different. Our phases are going to be slightly different. And so controlling all of this becomes very important when it comes to setting up very specific Hamiltonians to study. And so now I'm going to try and sell you a little bit on silicon carbide, of which some of you in this room have work on. And so I wanted to highlight some of the impressive work that's been done there, specifically because it plays into the strength of silicon carbide as a solid state platform. And really that lies in the maturity of the nanofabrication from silicon carbide itself, namely wafer scale CMOS compatible processing, as well as, I'm not really going to touch on this as much, but there's been a number of advances in high power electronics for silicon carbide, and as such, doping and the kind of semiconductor processes that go into silicon carbide and its growth and its doping and its design for electronics is also well known, and so this provides a relatively unique avenue to couple to defects. And of course, it hosts optically addressable spin qubits with long electronic coherence times. It's got optical emission in convenient wavelengths, and by convenient wavelengths, I mean in those where we can take optical fibers and connect them to other things with relatively low loss, so we can extract photons from this platform relatively easily, and has high temperature operation, aka you can do this in a closed circle cryostat at 4K. In fact, the defects that I've been working on primarily in my PhD, the Silicon Vacancy Center, can actually operate up to 10K to above. And this makes building devices much easier than having to use a dilution refrigerator. And of course, silicon carbide also, as a result of a lot of hard work from a lot of very intelligent people, now has excellent optical properties. So have low optical loss on the order of less than 5 dBs per meter, which is quite good, which means all of our photonics that we make now are no longer material limited. They're now nanofabrication limited. And there's also a strong bulk optical nonlinearity. And so I want to highlight that because, again, this is relatively unique to silicon carbide over the other solid state platforms for doing cavity QED, like diamond and silicon are the other two. And I suppose people are working on HBN these days too, but yeah, of these, silicon carbide is unique in that it has a strong chi3 nonlinearity, and so this lets you access Hamiltonians again that you could not reach otherwise with other materials. Excellent. Yeah, so the silicon vacancy is the color center of choice that I have been working on in Yellen's group, and that's primarily because of its interesting level structure and its excellent wavelength. It's a very convenient wavelength for working with lasers. We have tunable lasers. These optical transitions there too, because it's a spin 3/2 system. Optical transitions are at 916.4 nanometers, which is convenient for scannable, tunable lasers and for optical fibers, etc. And so, okay, so the level structure looks a little bit like this up here in the corner. There's a spin 1/2 and a spin 3/2 transition. These are optically accessible and spin preserving. There are two metastable states in the center with these intersystem crossings, and this is not great. So if you're comparing the silicon vacancy to other defects, the main issue really is going to be the cyclicity of these optical transitions. That provides a big issue because it limits the amount of times you can interrogate this quantum state before you potentially destroy it by accidentally swapping your spin state. So this is going to require to build the interesting quantum networks that I was describing before to do excellent readout of these states. It's going to require some careful photonic engineering. Additionally, because it's in silicon carbide and the location of the missing silicon atom in the V2 center, this is at the K site on silicon carbide, it's not inversion symmetric, which means that it is sensitive to first order electric fields, unlike some of the diamond defects, which are inversion symmetric, which kind of protects them from this first order electric field. And what that means is that for a long time, people actually believed that you would not be able to have stable defects within silicon carbide, stable optical lines, because the movement of charges within the silicon carbide itself will cause spectral diffusion and spectral wandering. But it turns out that with very careful growth, you can indeed, and careful electron irradiation to create these defects, you can create relatively stable silicon vacancies in silicon carbide. And so you can see that here. And then these have actually been then positioned within waveguides and then eventually resonators. And that's what you see from George's group and from our group here, which is relatively stable line width of silicon vacancy within photonic structure. Okay, so if you're doing cavity QED, you need a cavity. And for much of the much of the work in cavity QED in solid state platforms is often done with photonic crystals. And that's because they tend to have excellent Q over V, which again, if you remember that one of the parameters we're very interested in for the cavity QED system is the coupling strength between the defect and the cavity mode. And this scales as the quality factor over the mode volume. And as a result, photonic crystal cavities tend to have very low mode volumes. And so even with modest quality factors, you can reach this strong coupling regime. Very, very, very high Gs. Now, there's a reason, however, that we don't want to use photonic crystals. And in this case, it's because I mentioned that the spectral diffusion is a problem. And that's because of damages to the lattice. And as a result, and this scales with the amount of defects that you put in your silicon carbide itself. And so if you want relatively stable defects, or even just somewhat stable defects, you need to have low implantation dosages. If you have low implantation dosages, these are randomly implanted in your silicon carbide. If you have low implantation doses randomly implanted in your silicon carbide, they will not often end up in your cavity mode volume. And that's a problem because then you can't couple to them. So you can make wonderful cavities with excellent small mode volumes, but if there's no defects that live in the mode volume, it's useless. So for this reason, and because of some fabrication constraints, we decided to use whispering gallery mode cavities to host these defects for doing cavity QED. And this is also because, with the exception of Noda's group in Japan, making photonic crystal cavities that are rarely high quality factor is very difficult. It's not easy, and it's also extremely difficult to get it to match simulation. And so this is another reason why we chose to use whispering gallery modes, is because really the geometry is very simple. It's a circle, and your loss is basically dependent on just the scattering loss from the surface roughness and the bending radius. And material losses, which, as we said, silicon carbide has been developed to the point with which the material losses are relatively negligible. So as a result, we developed extremely smooth whispering gallery mode resonators using a photoresist reflow process. So by simply defining circles in photolithography. So first, sorry, let me take one step back, which is you can have an excellent surface finish on your silicon carbide, like kind of on insulator platform, by using chemical mechanical polishing on it first. So we can start with this 0.3 nanometer surface roughness on our silicon carbide, which is excellent. This prevents a large amount of scattering loss. And then we need to find a way to make sure that this transfers properly into the whispering gallery mode resonators when we fabricate them. And so that means this photoresist reflow process that I just mentioned, because this causes the photoresist to melt. The melted photoresist then has extremely smooth surface. So then when you use your reactive ion etch to transfer the pattern, you transfer the extremely smooth reflowed surface into the already relatively smooth silicon carbide. You maintain the surface roughness from the original CMP polishing step. And so from that, we've made several whispering gallery mode resonator designs. You see this mushroom here that's completely undercut, as well as this semicircle here that's suspended. So that means with whispering gallery modes and the silicon vacancy center, our cavity QED system looks a little bit more like this. Because the whispering gallery mode has two, for the most part, degenerate photonic modes, clockwise and counterclockwise modes. We now have this additional photon mode here. But this whole thing is passive. The defects have been implanted with electron beam radiation. There is moving charges in the silicon carbide, like I mentioned before. You saw that the spectral lines don't sit still. So that means is that these guys move around in frequency. And so there is interesting physics to be probed when your defects are moving around with this spectral diffusion. But it does severely limit the amount of explicit quantum information science that we can do. You can't really do gates if your qubits are moving around in frequency and they can't be addressed. And so I'm going to talk a little bit about the interesting physics that we saw in this passive system, but this is primarily as a way to kind of motivate that this is cool, but it gets more interesting when your defects sit still and you can control them individually. So we were able to take, so what you're seeing here in this nice movie is a waveguide coupled to this whispering gallery mode resonator. There are between 5 to 10 to even 17 defects within this resonator. And you can kind of see that from the autocorrelation and cross-correlation measurements that we've taken off of photons going the clockwise and counterclockwise modes of this resonator. This movie that you're seeing is actually a raster scan of above resonant light excitation to the cavity collected out of the coupled waveguide. And so by collecting out of the coupled waveguide, you get this spatial match, because when the laser's over here, it's exciting the defect, and then the defect's photoluminescence is projected into the cavity and then out. And what you're seeing as they kind of show up in time is gas tuning the cavity through several central frequencies. And that's why the defects are not all there at the same time, because again, like I mentioned before, this distributed environment, the moving charges in the environment, the changes in the lattice mean that not all of our qubits are the same. They're at different spectral positions and they move in time. So that's why you see this sweep through them. And then because the defects are in random positions around the resonator, and a moving time. This as a spectral disorder and a phase disorder between the defects within the cavity. We see this interesting like emergent chirality from the photon emission. So the photon emission, because of the way the phases tend to add up as you emit photons, the system will emit a photon first to the clockwise and then to the counterclockwise. And so you can see these correlations, and this is interesting. This is evidence that there is correlated behavior in the system because all of the defects are individually strongly coupled to the cavity mode. But there's not so much you can do with this other than say, okay, like this is evidence that something interesting is going on, but we can't really control it. We can't do gates. We can't do spin-photon entanglement because fundamentally, because the defects are moving around so much, we just have many two-level systems like randomly coupled at random times. And so you can see that here, which is by tuning the cavity with the gas tuning line, we can tune it to a regime where there's only a single defect strongly coupled to the cavity. But again, because of spectral diffusion, the time trace of this strongly coupled defect to the cavity mode doesn't show the expected Rabi oscillations. So if you're in any strongly coupled system, you should expect to see Rabi oscillations in population between your two modes. And we are within the regime where we'd expect this, but because the defect moves in time, every time we sample photons that come out of the system, we're actually averaging over many spectral detunings. And this kind of gives rise to this sad little knee instead of the Rabi oscillations that you would expect from a strongly coupled system. And so, if we were able to get this defect to sit still spectrally, and if we were able to control its center spectral position, we will be able to pick out, the proper Rabi oscillation here. We will be able to perform much more interesting entanglement schemes between these defects. And unfortunately, this is not out of the question. So while there are moving charges in silicon carbide that contribute to the spectral diffusion, there has been evidence in both the die vacancy and the silicon vacancy that by placing a diode structure around the around the defect in question, you can actually put the diode in reverse bias, sweep out the charges using a depletion region and the diode, and this will stabilize the defect's spectral diffusion. And so you can see this, Chris Anderson, in the die vacancy, and then more recently from Stuttgart, Timo's work showed that this can be done with a Schottky diode. Chris's work is with the PIN diode, so this is where that doping comes into play that I was talking about before. And we have significant, in our group, we've shown significant Stark tuning already. So we can tune defects up to 200 gigahertz. And so combined, and this is partially because of the lack of inversion symmetry, which allows us to tune them so far, compared to other platforms like Diamond, where it's much more difficult to tune defects this far. So we have here is that if we're able to incorporate this electrical control into our photonic cavities, then we will be able to have stable defects that we can tune to very specific places with respect to the cavity. And that's what we need. So I'm going to take a brief aside and talk a little bit, because I'm a sucker for nanofabrication. I'm going to talk a little bit about how we were actually able to couple to these cavities, because if you may have caught from before, the cavities are made with photolithography. Photolithography doesn't have the minimum feature size that enables us to actually couple a waveguide to a single mode waveguide to this cavity, because you actually just can't put it close enough. And now that's fine. People have done these kind of reflown resonators before in literature. Specifically, Kari Valhalla's group did this almost 20 years ago. But they did this with a tapered optical fiber. So by taking an optical fiber and melting it and pulling it, they were able to cause the optical mode in the optical fiber to extend and then evanescently couple to their whispering gallery mode cavities. And we tried this, and it does this in the cryostat, because the mechanical vibrations from the cryostat that are required to keep the defects down at 4K, to keep their spin coherence, causes so much vibrations that the tapered optical fiber acts like a giant guitar string and will not sit and controllably couple to our whispering gallium resonators. And so this makes running experiments extraordinarily difficult. And in addition, the index of the optical fiber means that this is undercoupled to the cavity mode, and you can't ever actually overcouple. And you know, part of what would be nice is if we could control the coupling to the cavity mode, because this allows us to interrogate the system in different regimes. So what did we do? We put together a silicon carbide based waveguide probe, a completely separate chip to bring close to the whispering gallium mode resonators. And by bringing this separate chip close by and then actually touching the silicon carbide waveguide on this chip to the resonator like so, we can control the optical coupling to the resonator system. So that's what you're seeing here is actually with the piezo stacks in our cryostat physically moving the resonator with respect to the waveguide on this kind of optical probe. And you can see us go through undercoupled to critically coupled to overcoupled to then actually we're starting to undercouple to the next higher order fundamental mode up on the mushroom cavity, which you see here. And so this is a silicon carbide waveguide placed on a silicon handle. And so this is like this nice little GDS design that you'll see here. But, you know, in practice, that means making a separate chip with a silicon carbide waveguide with suspended silicon carbide waveguides on it, gluing tapered fibers to them, removing this from the previous chip, and then placing it down on that silicon handle from before. And this is the nice schematic, but this is what it looks like when I do it in the lab. There's, you know, all these wonderful hand micrometers where we can bring the tapered fibers close to the waveguide. These are actually images from previous waveguide designs. You'll notice that this kind of bend is here because when you cool down the this like probe system, there's enough thermal expansion that you need this strain relief bend to prevent the optical fibers from actually ripping the silicon carbide apart. Because while it's a strong material, there's only 400 by 400 nanometers of it in a waveguide, and so there's only so strong that it can be. And so yeah, so this is the process of assembling this thing together. We put some UV cure epoxy on it to kind of hold everything in place. The whole assembly goes in the cryostat nicely. This is a S50 Montana cryostat, so it's quite small. This is not that large. I would say, let's see, the chip's about this big, so maybe about that big. And then through simply optical access from the top, you can see the waveguide with respect to the optical to these whispering gallium mode cavities. And by moving the piezo stack that holds the chip under test, you can controllably optically couple to these designs. So that's great, but that's just optics. And as I mentioned before, we want to do electronics as well. We would like to electronically control the same devices by providing some DC bias to be able to do this depletion diode stuff that I mentioned before. And so this can actually all be done on the same chip. And this is, adds the advantage that you can test many optical resonators with the same outcoupling technique. So this here is an example of extremely simple photonic device. This is just a whispering gallium mode resonator with a patterned on gold wire next door. This is a 4-point probe measurement, which means you literally just run some current. You can measure the voltage. It gives you the resistance. And as a result, you can just thermally dump some heat into this resonator. The heating of the silicon carbide will cause the refractive index to change. That's what you see here, is that by very carefully kind of aligning these extended electrodes off the tip of the probe, we're able to both optically and electrically control a number of devices. And this works at both ambient temperature and at cryogenics, although the thermal optic tuning of silicon carbide is less at cryogenics, so it required a bit more power. And this is kind of what it looks like from above. You can see the waveguide here and the electrical line sticking down. the electrical tines, of course, need to touch before the optics touch, because if you remember from the way that these resonators look, there's a bump that's the whispering gallery mode resonator, and then these electrical lines that are underneath. And so that means that with some very careful strain tuning on the electrodes themselves, we're able to cause them to actually bend. So this is a little bit difficult to see, but if you look closely at this SEM, you can see that the electrical tines actually bend up to about 20 degrees past. And so this means that when you flip this whole assembly upside down and then attempt to couple to an optoelectronic device, the electrical tines will touch before the waveguide will, and you'll get electrical contact and then optical contact. And this kind of additional pressure keeps it down, even with the cryostat vibrating. And so this is some SEMs and then an optical image of the same thing. So that's great for very simple devices, but how do we make the device to do stable defects within whispering gallery mode cavities? And that looks a little something like this. So I should have probably started with this a little earlier. We're working with silicon carbide on insulator as the platform. We do this fabrication in-house. And this is a silicon carbide chip on top of silicon oxide, a thin layer of silicon oxide. This is about 400 nanometers. This is actually to scale, this PowerPoint drawing, on top of silicon. And so if we want to make this whispering gallery mode resonator that you saw before, this kind of suspended membrane, then we want the optical mode to travel around this way. We need to be undercut so that the silicon doesn't destroy the optical mode. And then we need to apply an electric field in the correct orientation such that it tunes the silicon vacancies. Because of the way the lattice is oriented, this is actually C-plane for a silicon carbide. And so the electric field needs to point up out of plane with the silicon carbide such that you properly tune the defects. If you apply the field in the other direction, you actually only get the second order tuning, and so it's significantly less. So if we want to be able to tune this 200 gigahertz to really be able to move defects around and match them up with the cavity, then we need to be able to apply the field up and down. And so this is slightly non-trivial, and so it requires being able to put an electrical contact on the center of that whispering gallery mode resonator that we saw before, and that's why you see this like horrendous looking metal bridge, which is actually, if you take a page out of the superconducting qubit community, this is done fairly regularly, and so we can implement this within these resonators with very good yield. But making these devices, the material that we use to host the defects, the silicon carbide, is relatively rare. We get it from one specific guy in Sweden, a collaborator of ours. And as a result, all this testing to make this harebrained electrical optical device together should be done ideally with silicon carbide that's not as rare, with materials that I can spend a lot of time in the fab ruining and have it not be a problem. And so it turns out that very conveniently, this electric field orientation that will tune your defects is also the same electric field orientation that applies the electro-optic tuning of silicon carbide itself. This is along actually the extraordinary axis of C-plane silicon carbide. And so I took a quick detour by demonstrating and measuring the electro-optic tunability of 4H silicon carbide as a proxy for determining whether or not these devices will work for tuning defects. So because of the crystal structure for 4H silicon carbide, you can drop out a number of the electro-optic like tensor coefficients. And so you basically boiled something fancy from the applied electric field in X, Y, and Z here. This is actually the even simplified form, because each of this K is actually a summation over 3 of these equations where K is X, Y, or Z. And so then you drop some crystal symmetry in there, you get a tensor that looks like this. So that's why you go down to 18 instead of 27 tensor elements. From here, then okay, the silicon carbide crystal crystalline structure from 4H has this 6 mm symmetry, so you can drop even more coefficients, and then you're left basically with just these guys, which means there's three coefficients that matter. The Z, like ZX, ZY, ZZ, and then like XZ. And so in the resonator design that I just showed you, you could simulate the electric fields and take a look at the TE and the TM modes. And because the modes have different electric field orientations, they should behave differently under an applied electric field in terms of electro-optic tuning. And so this is an example of the TE and the TM mode in this whispering gallery mode structure. And this is the static electric fields that are applied when you apply static voltage on those electrodes that I've shown. And so I was able to fabricate these guys. So this is the bridge showing before that allows us to put a different field here versus there. This is slightly complicated to extract the electro-optic coefficients from, actually, because not only is the radial electric field profile not the same all the way around, because we actually need to bring that waveguide in to couple to these devices, right? And so if you put the metal contact where the waveguide is, you'll kill your optical mode, and you actually won't couple to the device. So you need to leave some region here open so that you can bring your waveguide in to couple to the whispering gallery mode resonator. And then you actually also need this little bridge here to be able to get your center pin to the right potential, which means the applied electric field around the resonator is not radially symmetric. Because it's not radially symmetric, makes some of the calculations a little difficult. What additionally adds complexity here is that if you look at this, there is both EZ and ER components. And so for most, and for others, there's another group at CMU, I believe, that's doing electro-optic tunability of 4H silicon carbide. They've built resonators and they've built modulators. They're very good, but they're only applying fields in the Z direction. And as I showed kind of before here on the Pockels coefficients, these guys are also in the X direction. And so because of this waveguide and resonator geometry, you're applying fields in both the X and the Z direction, adds a significant amount of complexity to exactly what's going on with the electro-optic shift. But nevertheless, we're still able to measure the electro-optic shift of these cavities by applying an AC field. So interesting enough, actually, there's a DC screening effect from the metal contacts being Schottky contacts to the silicon carbide that causes a DC screen. So you actually don't see electro-optic shift when you apply a static voltage, but you will see when you apply an AC voltage. And so we saw electro-optic shift of the cavities up to 70 megahertz. And this is actually limited by our cryostat wiring, not by the device itself. And then to further extend this, yeah, okay, so this is in whispering gallery modes with a quality factor of 800,000. And these ones are rather large. This was actually with about 25 micron diameter. So this is a large whispering gallery resonator with relatively good quality factor. We see the linear shift as a result of applied voltage. This is for 30 kilohertz. We see electro-optic tunability up to 70 megahertz, but this is not, again, not limited by our devices. And indeed, we actually put up to 200 volts across this gap right here. This is an 8 micron gap. And indeed, that actually was not the problem. So what you see here is the blown up electrical tines from the waveguide probe that we use to couple to these devices, which implies that, as expected, kind of silicon carbide has a very high breakdown voltage. And so you can really apply a lot of field across this direction, which is excellent for our goal of tuning defects within cavities. So this is great. The electrode design works. We can couple it to these optical cavities. Time to make devices on quantum grade material. which is what I've been doing for the last couple weeks. So unfortunately, I was hoping to be able to tell you guys, yeah, we have stable defects in cavities. Everything is great. But I haven't measured them yet, actually. They're cold in the cryostat right now. This is what the devices look like. As you can see, the same kind of geometry with these undercut holes from before. Preliminary measurements show, unfortunately, lower quality factors than I was hoping. This is for a 10 micron diameter device, the quality factor of 95,000. This is because I put the electrodes a little too close. So instead of being separated by 8 microns, these are instead separated by 6. And so that's a little too close to the optical mode. So you get this loss from the electrodes here. But actually, this should be completely sufficient to see defects within the cavities. And so the devices you can see loaded. These are measurements from room temperature. It's cold now. So I will be measuring those in the coming weeks. And hopefully I will be very excited to tell you guys about it. But to kind of sum up, really, I guess what I want to impress upon you guys today is that it's advances in nanofabrication that have enabled us to get to interesting places in solid state cavity QED systems. And that by continuing to push these nanofabrication steps even further to add integrated electrical control, we can open even further doors in what we can do with cavity QED. And this is really going to come from integrating electrical control with optical control so that we can have stable defects within cavities. Yeah, and I'm excited to bring you those results when they happen. These are some nice optical images of the devices themselves. You'll notice that while this is a very pretty picture, this is actually because of the thickness film uniformity in our devices. And so that's a little sad, but it looks nice. So with that, I want to thank all of the many people in Yala's group and other groups that we collaborate with that have helped me with this work. And thank you all of you for listening. And I'm more than happy to take questions.
Thank you, Dominic, for a great talk. Questions?
Yeah.
As like you guys are making like Schottky diode, wouldn't the like the
Yes.
deflection region would be very small, like
Ah.
compared to like PIN, like to
This is true. Yeah. So your can I draw on? Yeah. So if you look at the design, it looks a little bit like this. If you put the PIN junction in, like you see in Chris Anderson's work, you get the depletion region starting kind of from these like carrier regions. But actually, lateral doping of thin film silicon carbide is not easy. And so we had some ideas about doing vertical doping. But actually, team of work that I showed here,
they also make Schottky diode.
they use Schottky diode. Oops, no, it's the wrong way. Sorry about that. Where's my mouse? Yeah, they use Schottky diodes, and they actually see depletion up to, I believe, 20 microns away from their contacts. So they can put a ton of voltage through these things because, again, silicon carbide has a really high dielectric breakdown. So you can really extend this depletion region really far. And so from our cavity designs, this is 8 microns apart. 20 microns is plenty sufficient to get the depletion region to where it needs to be.
And also like because like let's say in optoelectronics books it said
Mhm.
like for like the electron to go from like the metal dielectric junction. So it's kind of like, do you think the doping matters like in silicon carbide?
It absolutely does. And this is why we have Schottky contacts and not ohmic contacts, is because we're using the material that we're using is as lightly n-doped as possible, because there is like the HPSI stuff that you can buy from Korea and stuff. These guys do like dopant like compensations. So they'll put p dopants in to kind of give you an intrinsic silicon carbide, but these dopants are bad for defects, right? Anything you have that's not your perfect crystal lattice is bad. And so we use this extremely lightly n-doped And by lightly n-doped, I mean 10 to the 14 n-dopants per centimeter. And so as a result, all the contacts will be Schottky contacts. So this actually does make the diode look a little weird. So if you look at this work, it's a Schottky contact on like epitaxially grown, nice, lightly n-doped silicon carbide on like substrate that is more heavily doped. And so that more heavily doped region has an ohmic contact on the bottom, so they get a nice IV curve. But if you imagine, this contacts that I've made, you'll get some diodes pointed at each other. And so it actually has this terrible looking IV characteristic. But that's okay, again, because you only need the depletion region part. Yeah.
How do you use the depletion region for your advantage in this case?
So the reason that the defects move in time is because of moving charges within the silicon carbide lattice, electrons and holes. So if you provide a depletion region, you quite literally sweep out all of the electrons and holes in that area. And so fortunately, this doesn't actually destroy the defect, because you can imagine that, if you really got rid of all the electrons and holes, then you would get rid of the defect too. But the defect state is strong enough that this doesn't happen. And so you just remove all of these moving charges, and by removing all the moving charges, you no longer have stray electric fields close by that tune your center frequency. And actually, this comes from really the optical light shuffling the moving charges around. So if you can imagine, like, just having this thing sit there in the dark, it will stay on the same position, because it's down at 4K, the electrons and holes don't move around that much. But as soon as you add the optics to do the optical readout of the spin states, then you start shuffling things around because of the energy from the photons. And that's no good. Yeah.
I found it very interesting that you're making resonators without undercutting them fully, like that they're connected.
Yes.
What designs were you considering? What are some other things that you thought may work for this? To keep that contact, but still have a vacuum.
Yeah, so that's a great question. Because this thickness here, like, really matters, right? If it's too thick, you lose your whole mode. But you need it to be thick enough that you can actually apply any fields. So really, we mostly targeted this kind of suspended structure here, especially since if you wanted to do electro-optic tuning of your whole resonator, this is no good, because you would need to put the metal contacts in this region. But if you only care about tuning defects, and if you only care about tuning defects in a specific location on the resonator, which is another advantage to the whispering Gallagher resonator, right? As you have spatial addressment from the top. You could just put the contacts here and here and here and here, and then you have individual control. We thought a little bit about doing like some pillar underneath, or some like awful electrical contacts prior to bonding and then bonding afterwards. But really, this is the most straightforward. And the undercut is actually not that bad, because it's on oxide on silicon, so you can do HF vapor for the silicon of the oxide layer, and then you can do like xenon difluoride for the silicon layer, and it's completely fine. I will say that we use HSQ for that oxide layer, and so the HF vapor goes through it like a hot knife through butter.
How thick is it in the end, roughly? What do you think?
So actually, if you look at the thin film colors on the chip that I showed, you can see it, right? Because each fringe is 50 nanometers. And so over here, there's actually no devices left because it's completely gone. But then as you go up, you can see you go from 50 to up to like 150. And target was really 50 nanometers, because that's nice and thin. But the mode will stick around up to 150. So yeah.
One more.
Yeah, of course.
So,
of course, please.
Between the electrodes, like how the electric field passes. So let's say, what is the tolerance between like the electric field lines and also like the optical mode. Like
Yeah. So this is what I ran to with my quality factor, right? So like before, when we were pushed out at 8 micron separation here between this and this, the quality factor is unchanged, which means there's no interaction between the electrodes and the optical one. But as soon as I brought them in another 2 microns closer, we see a drop in the quality factor by a factor of 4, or sorry, a factor of 8. And so, this is evident that even out here, and it's actually probably this one. It's not the one out here. It's really the one in the center that's impacting the optical modes there. But this is actually another reason to be careful with PIN doping, is because those doped regions will kill your optical mode as well.
Yeah. Photonics needs to be in the intrinsic layer.
Exactly.
Exactly.
Yeah. No electrodes.
So, and all of this, like you could simulate in console, right?
Yeah. Well, the difficult part with that is if you look at this guy, this thing is huge, right?
Yeah.
And so you can't actually easily simulate the optical mode going around this whole thing. So to extract the applied electric field actually took several
Slice like this, yeah.
exactly, and then extrapolate the slices. So yeah, you can do it with COMSOL. It takes a little bit of work.
So you have this very fancy electrical optical probe.
Yeah.
Have you thought at all about ways to have integrated photonic addressing?
Yeah, so the nice part about all of this is that I can actually still claim that all of this is scalable, because if you have a deep UV stepper system like TSMC, then you can make with photolithography and reflown photoresist all of these feature sizes. So you can just put the waveguide right on the chip and you're completely good to go. But I don't have one of those.